In this video, I want to continue talking about functions with more than two variables. We've been talking about planes, which has three variables. Actually, there's only two, right? Because once you figure out what x and y are, z is fixed, so z is more of the dependent variable. So in this video, I want to talk about basically how to plug and chug some of these things. We want to talk about the domain of these functions. We want to talk about how to graph them. Actually, we're going to talk about how to get software to help us graph these, because graphing these are kind of a pain in the ass. We'll be looking at something called a contour graph, which will help us get an idea of what it should look like. And then we're going to talk about some limits, because we're going into calculus, and calculus is all about limits. Without further ado, let us get started. First off, let's consider the function f of xy is equal to the square root of x plus y plus 1 over y minus 2. So what we want to ask ourselves is, what can I stick in there? Like all the domain questions, what can I stick in there without it going crazy, without it blowing up in my face? So if f of xy is equal to the square root of x plus y plus 1 all over y minus 2. Now, when you talk about domains back and way back when, you were looking at one axis, the x-axis. What from the x-axis can be stuck into the function? Well, here we're looking at the plane, because x and y points will determine the z value. So I want to know what points on the plane can I stick into this function. Well, one thing I know I can't put in here is any time that y is equal to 2, because that gives me a 0 on the bottom, world blows up, not a good thing. The other thing is x plus y plus 1 must be greater than or equal to 0. 0 is okay because we can have 0 under the radicals. So let me solve this. I have y is greater than or equal to negative x minus 1. Graph this. This is the edge of our region. It's a line. So I'm thinking of the line y equals negative x plus 1. Negative x minus 1. So it goes through here. It goes through 1. Being the nerd that I am. So this divides the xy plane into two parts, two half planes. So the question is, which one can I use? The easiest way for me to check is to say, okay, here's 0, 0. If I plug 0, 0 in here, is that okay? Well, it's the square root of 1. That side is okay, so 0, 0 is in the domain. So all of this region is where x plus y plus 1 is greater than or equal to 0. Now we also have to throw away where y equals 2. I'm just going to put like a dotted line here. Don't need to go that way because we've already thrown that part out. So that's the domain of this function, is anything up here in this half plane that's colored except for what's on the purple dotted line. Let's look at the next one. Suppose we have f of xy is equal to x plus 3y plus 2. What's the domain? Is there anything I can't stick in there? I mean, any real number? I mean, I can't stick a hippopotamus in there because that would be weird. But I can stick any real number in there. So the domain for this is all of r cross r, or r2. X times the natural log of x squared minus y. X in the front I don't care about. What I do care about is this x squared minus y. I can only plug positive things in a natural log. So I have natural log of x squared minus y. That means x squared minus y must be strictly positive. Can't equal 0 either. So that means y is less than x squared. Graphing this. I know that I have x squared, our average Joe parabola. Now, pretend that's a parabola. Y has to be less than x squared. Okay, so I'm going to pick something like it's either going to be inside the parabola or outside the parabola. If I stick in, let's say this is 1, 0. If x is 1 and y is 0, this statement is true. This is the domain of that function. How do we see what they look like? I'm going to show you how to do it in Maple, but I also want to show you how to do it in Desmos, I didn't like Desmos because you couldn't move things around, but I do like GeoGebra. What did I say? You should be able to get to Maple from the computers on campus. You should be able to download them or use them in the labs, either way. So we need to fill in the commands for plots. So I've got with plots. I want to plot, this is x squared plus y squared. And I said x is going from -3 to 3, y is going from -3 to 3. Let's see what that looks like. Let's make it a little bit bigger. This looks like, I don't know, a little parachute. Looks like a full diaper. You can tell I'm a mom. So it looks, yeah, that's what it looks like. Something like that. Now, if I were to try to look in GeoGebra, so this is a 3D, oh, look, it's very sensitive. I'm grabbing it and flopping it around and it's making me a little queasy. So this is the three space. Now I've already put in a couple things here. Here's I put in the sphere, or the top of the sphere. It's trying to render it, but it gets a little weird near the edge. But you can see how that graph, the graph of x squared plus y squared, oh sorry, the square root of 25 minus x squared. Stop spinning! Jeez. The square root of 25 minus x squared minus, that's supposed to be a y squared, gives me this. What's the one we just did? We actually did something different than the other one. I had x squared plus y squared. And, oh, looky, I got them together. It's like a really bad glass. Let's get rid of this one. This gives me a much better idea of what that shape is, rather than the full diaper look. Okay. So we have kind of a cone. It's a little bit smooth on the bottom. So that's what that picture looks like. Another thing we like to do is a contour graph. What does it look like when x cubed minus y is equal to 0? Or what happens when x cubed minus y is equal to 1? We let our z value be different things to see what's happening on that slice. So x cubed minus y, I know if z equals 0, that's going to be a cubic. So what this is doing is saying what's happening if you have x cubed minus y equals 0. Well, then you've got a cubic. It's actually not putting that cubic in there because that's not one of the ones I hit. But if I put my cursor on it, it tells me which one I'm looking at. This is where I have x cubed minus y is equal to negative 0.222. And this is where it's equal to negative 0.66 and positive 0.222. We can also try to do this by hand. So what I mean by that, so we have f of xy is equal to x cubed minus y. So if I let my z equal to -2, -1, 0, 1, and 2. Let's look at that. So what do I get at these different z values? Well, x cubed minus y is equal to, let's do the easiest one, 0. So that means y is equal to x cubed. Average cubic. If I have z equals 1, I have x cubed minus y is equal to 1. So y is equal to x cubed minus 1 if I solve for y, which is the same average Joe cubic, but it's shifted down by 1. And I go like that. And it's supposed to be symmetric. I can't draw. So you can see what's going on. As z changes from these different points, your cubic is just going to be higher or lower on the graph. What about this graph? What if we have f of xy is equal to the square root of y squared minus x squared? It's got to be positive because it's a square root. Let's see what Maple tells me. Oh, what's the domain of that? I have to be careful. Y squared minus x squared must be greater than or equal to 0. Y squared must be greater than or equal to x squared, which means we have, if I take the square root of both sides, you have to think that it's plus or minus when you take the square root, and then you switch the symbol here. So I know my line's going to be based on y equals plus or minus x, which is this line and this line. So what sections am I going to be able to use? Well, I want y squared greater than x squared. So if y squared here, because y gets bigger and x is 0, this is where y squared is greater than x squared. And the same thing down here. So that's the domain of my function. So cool. So you can see how it is following those lines we had when we said the domain was the top, whatever you call that, quarter plane and the bottom quarter plane. It gets a little freaky over here. It loses its mind, but that's okay. It's allowed to lose its mind. Okay, so we have the square root of y squared minus x squared has to equal a z. And z can be various numbers. So I'm just going to say, call it k, where k is some constant. If I square both sides, I get y squared minus x squared equals k squared. And if I divide, so that it looks like, oh, that's the graph of a hyperbola. Can I spell it? Hyperbola. So that's what you're seeing in that other picture, are all these little hyperbolas that just get wider and wider. Now let's talk about limits. Let f be a function of two variables whose domain D includes points arbitrarily close to a comma b. So we're going to get closer and closer to a, b. Then we say the limit of the function as xy approaches this a, b is some number L. And we write that contraption xy heads to ab of f of xy equals L if and only if for every epsilon greater than 0 there exists a delta greater than 0, such that if xy is in the domain and 0 is less than the square root of x minus a quantity squared plus y minus b quantity squared is less than delta, then the absolute value of f of xy minus L is less than epsilon. What the fuck are we saying here? Okay, what this is saying in English, hopefully, when you did limits in Calc 1, you only had to do, so here's your function, here's my a, here's the limit. So we were worried about closing in on a and getting next to L. So as long as, if you chose something really close to L, like L plus epsilon, L minus epsilon, I can find a delta so that I'm within delta of a, and I plug it into the function, I will hit the target. I will be able to get in that spot. The problem with 3 space is interval here is now a circle. And I can't draw it because I can't draw circles. But if I have, here's my point that I'm trying to get closer and closer to. As I get closer and closer to this point, then whatever the value of the function is up here is going to get closer and closer to my L. That's what all that is saying. We're not going to do any delta epsilon proofs, especially not in 3D, but I wanted you to see what the definition is. The idea is, as you close in on something, and the key is you have to close in on it from every direction, not just one line. And I'll show you what I mean by that. Here's a limit. Let's say I want to figure out the limit as xy approaches 0, 0 of x squared minus y squared over x squared x squared plus y squared. We can see 0, 0 is a bad point here. It's the only bad point in this function. Whatever the function looks like, 0, 0 is not a good function. Let's see if we can prove that this limit doesn't exist. So if I have the limit as xy approaches 0, 0, and at some point I might just start saying x bar is approaching 0 bar, so I don't have to write so much, of x squared minus y squared over x squared plus y squared over x squared plus y squared. Okay, so let's see. I can approach it, if I approach it along the line here where y equals 0. So as I approach it on this line, if y equals 0, then what I'm getting is the limit of x squared over x squared then what I'm getting is x squared over x squared, which is just 1. Cool. Let's approach it along the line x equals 0. So I'm approaching it, I'm closing in, can't see what I'm closing in using the y-axis. So this is going to give me the limit of all that shit. X is 0, so I've got negative y squared over y squared. This is negative 1. Remember when we said back in Calc 1, if the limit from the left doesn't equal the limit from the right, then the limit doesn't exist? In 3-space, we've got infinitely many ways we can approach our point. But it doesn't matter, as long as there's 2 points or 2 approaches that are different, the limit doesn't exist. So I've got 1 going from one direction, negative 1 coming the other direction, so this limit does not exist. We have the limit as x approaches 0, because that's going to be the easiest one to do, of xy over x squared plus y squared. Again, 0, 0 is the bad point. We can't put 0, 0 because we'd have 0 in the denominator. I also can't let x equal 0, y equal 0, because both times I'm going to get a 0. What I could do, though, is say, let x equal 0, in which case my limit of xy over x squared plus y squared is equal to 0. Now let's try something different. Again, remember, I can approach this by x squared, or that's an x cubed. I can approach it by x. I can approach it from any direction. I'm going to approach it by letting x equal y. So that gives me x equals y. I have x squared on top. I have 2x squared on bottom, which is equal to 1/2. Not equal, so the limit doesn't exist. So the only place we need to worry about whether a function is continuous or not is on the edge of its domain. Okay? And it's not going to be continuous if it's not in the domain, because you can't be continuous if you're not there. So let's look at an example. Let's say we've got the cosine of the square root of 1 plus x minus y. So I'm trying to find the domain of this to figure out where it is continuous and where it is not continuous. Why is this not in focus? So we have the cosine of the square root of 1 plus x minus y is my function. So 1 plus x minus y must be greater than or equal to 0. This is under the radical. So I have y is less than or equal to x plus 1. So that's the only place we can't plug this stuff in. So drawing my picture. X plus 1, I go through 1. Slope is 1, I go through negative 1. Oh, solid because it's or equal to. Y has to be less than that. If I stick 0, 0 into this, I get 0 is less than 1. So that's the domain. So the only place this function is not continuous is along this line, because you can't have the function for this side and this side because the function doesn't exist here. Let's look at this one, h of xy. Looking at this, the only place that's bad is when we have 0 in the bottom. So when e to the x times y equals 1. Places we don't like, let's see, e to the x. X times y not equal 0. Well, the only time it's going to equal 0 is when x equals 0 or y equals 0. The domain of this function is everything except for the xy axis. This is where x is equal to 0, and this is where y is equal to 0. So we have to toss those points out. What we've looked at is functions in 3-space. They're not that much different than functions in 2-space, except they're sometimes harder to see what they're going to look like. The contour graphs help us get an idea by kind of looking at slices. Just plug it into Maple, it gives you a really good idea of what it looks like. So in the next video, we'll be actually talking about the calculus, how to find the slope of the curve, And again, we've got to do this coming from two different directions, because just because it's a maximum this way doesn't mean it's a maximum that way, or you could have some other weird ass shit going on. That is a good place to stop.